Asteroid.
Asteroids are minor planets, especially those of the inner solar system. The larger ones have also been called planetoids. These terms have historically been applied to any astronomical object orbiting the Sun that did not show the disk of a planet and was not observed to have the characteristics of an active comet, but as minor planets in the outer solar system were discovered, their volatile-based surfaces were found to resemble comets more closely and so were often distinguished from traditional asteroids. Thus the term asteroid has come increasingly to refer specifically to the small bodies of the inner solar system out to the orbit of Jupiter. They are grouped with the outer bodies, centaurs, Neptune trojans, and trans-Neptunian objects, as minor planets, which is the term preferred in astronomical circles. In this article the term asteroid refers to the minor planets of the inner solar system. There are millions of asteroids, many thought to be the shattered remnants of planetesimals, bodies within the young Sun's solar nebula that never grew large enough to become planets. The large majority of known asteroids orbit in the asteroid belt between the orbits of Mars and Jupiter, or are co-orbital with Jupiter, the Jupiter Trojans. However, other orbital families exist with significant populations, including the near-Earth asteroids. Individual asteroids are classified by their characteristic spectra, with the majority falling into three main groups: C-type, S-type, and M-type. These were named after and are generally identified with carbon-rich, stony, and metallic compositions, respectively. Only one asteroid, 4 Vesta, which is a relatively reflective surface, is normally visible to the naked eye, and this only in very dark skies when it is favorably positioned. Rarely, small asteroids passing close to Earth may be visible to the naked eye for a short time. As of September 2013, the Minor Planet Center had data on more than 1 million objects in the inner and outer solar system, of which 625,000 had enough information to be given numbered designations. On January 22, 2014, ESA scientists reported the detection, for the first definitive time, of water vapor on Ceres, the largest object in the asteroid belt. The detection was made by using the far-infrared abilities of the Herschel Space Observatory. The finding is unexpected because comets, not asteroids, are typically considered to sprout jets and plumes. According to one of the scientists, the lines are becoming more and more blurred between comets and asteroids.
Naming.
A newly discovered asteroid is given a provisional designation, such as 2002-84. Consisting of the year of discovery and an alphanumeric code indicating the half-month of discovery and the sequence within that half-month. Once an asteroid's orbit has been confirmed, it is given a number, and later may also be given a name, for example 433 Eros. The formal naming convention uses parentheses around the number, for example, 433 Eros, but dropping the parentheses is quite common. Informally, it is common to drop the number altogether, or to drop it after the first mention when a name is repeated in running text.
Symbols.
The first asteroids to be discovered were assigned iconic symbols like the ones traditionally used to designate the planets. By 1855 there were 24 asteroid symbols, which often occurred in multiple variants. In 1851, after the 15th asteroid, Eunomia, had been discovered, Johann Franzenk made a major change in the upcoming 1854 edition of the Berliner Astronomisches Jahrbuch, BAJ, Berlin Astronomical Yearbook. He introduced a disk, circle, a traditional symbol for a star, as the generic symbol for an asteroid. The circle was then numbered in order of discovery to indicate a specific asteroid, although he assigned to the fifth, Asteroid, while continuing to designate the first 4 only with their existing iconic symbols. The numbered circle convention was quickly adopted by astronomers, and the next asteroid to be discovered, 16 Psyche, in 1852, was the first to be designated in that way at the time of its discovery. However, Psyche was given an iconic symbol as well, as were a few other asteroids discovered over the next few years. See chart above. 20 Massalia was the first asteroid that was not assigned an iconic symbol, and no iconic symbols were created after the 1855 discovery of 37 Fides. That year Asteroid's number was increased to, but the first 4 asteroids, series to Vesta, were not listed by their numbers until the 1867 edition. The circle was soon abbreviated to a pair of parentheses, which were easier to typeset and sometimes omitted altogether over the next few decades, leading to the modern convention.
Discovery.
The first asteroid to be discovered, Ceres, was found in 1801 by Giuseppe Piazzi, and was originally considered to be a new planet. This was followed by the discovery of other similar bodies, which, with the equipment of the time, appeared to be points of light, like stars, showing little or no planetary disk, though readily distinguishable from stars due to their apparent motions. This prompted the astronomer Sir William Herschel to propose the term asteroid, coined in Greek as asteroids, asteroid star-like, star-shaped, from ancient Greek asteros star, planet. In the early second half of the 19th century, the terms asteroid and planet, not always qualified as minor, were still used interchangeably. For example, the Annual of Scientific Discovery for 1871, page 316, reads Professor J. Watson has been awarded by the Paris Academy of Sciences, the Astronomical Prize, Lalande Foundation, for the discovery of 8 new asteroids in 1 year. The planet Lydia, No. 110, discovered by M. Borrelly at the Marseille Observatory. M. Borrelly had previously discovered 2 planets bearing the numbers 91 and 99 in the system of asteroids revolving between Mars and Jupiter.
Historical methods.
Asteroid discovery methods have dramatically improved over the past 2 centuries. In the last years of the 18th century, Baron Franz Xaver von Zach organized a group of 24 astronomers to search the sky for the missing planet predicted at about 2.8 AU from the Sun by the Titius-Bode law, partly because of the discovery, by Sir William Herschel in 1781, of the planet Uranus at the distance predicted by the law. This task required that hand-drawn sky charts be prepared for all stars in the zodiacal band down to an agreed-upon limit of faintness. On subsequent nights, the sky would be charted again and any moving object would, hopefully, be spotted. The expected motion of the missing planet was about 30 seconds of arc per hour, readily discernible by observers. The first object, Ceres, was not discovered by a member of the group, but rather by accident in 1801 by Giuseppe Piazzi, director of the Observatory of Palermo in Sicily. He discovered a new star-like object in Taurus and followed the displacement of this object during several nights. His colleague, Carl Friedrich Gauss, used these observations to find the exact distance from this unknown object to the Earth. Gauss' calculations placed the object between the planets Mars and Jupiter. Piazzi named it after Ceres, the Roman goddess of agriculture. 3 other asteroids, 2 Pallas, 3 Juno, and 4 Vesta, were discovered over the next few years, with Vesta found in 1807. After 8 more years of fruitless searches, most astronomers assumed that there were no more and abandoned any further searches. However, Carl Ludwig Heinz persisted, and began searching for more asteroids in 1830. 15 years later, he found 5 Astia, the first new asteroid in 38 years. He also found 6 Eb less than 2 years later. After this, other astronomers joined in the search and at least 1 new asteroid was discovered every year after that, except the wartime year 1945. Notable asteroid hunters of this early era were J. R. Hind, Annibal de Gasparis, Robert Luther, HMS Goldschmidt, Jean Shakornak, James Ferguson, Norman Robert Pogson, E. W. Temple, J. C. Watson, C. H. F. Peters, A. Borrelly, J. Palisa, the Henry brothers and Auguste Charlois. In 1891, Max Wolf pioneered the use of astrophotography to detect asteroids, which appeared as short streaks on long-exposure photographic plates. This dramatically increased the rate of detection compared with earlier visual methods. Wolf alone discovered 248 asteroids, beginning with 323 Brucia, whereas only slightly more than 300 had been discovered up to that point. It was known that there were many more, but most astronomers did not bother with them, calling them vermin of the skies, a phrase variously attributed to Duarte Suess and Edmund Weiss. Even a century later, only a few thousand asteroids were identified, numbered and named.
Manual methods of the 1900s and modern reporting.
Until 1998, asteroids were discovered by a four-step process. First, a region of the sky was photographed by a wide-field telescope, or astrograph. Pairs of photographs were taken, typically 1 hour apart. Multiple pairs could be taken over a series of days. Second, the two films or plates of the same region were viewed under a stereoscope. Any body in orbit around the Sun would move slightly between the pair of films. Under the stereoscope, the image of the body would seem to float lightly above the background of stars. Third, once a moving body was identified, its location would be measured precisely using a digitizing microscope. The location would be measured relative to known star locations. These first three steps do not constitute asteroid discovery. The observer has only found an apparition, which gets a provisional designation, made up of the year of discovery, a letter representing the half-month of discovery, and finally a letter and a number indicating the discovery's sequential number, example, 1998 FJ74. The last step of discovery is to send the locations and time of observations to the Minor Planet Center, where computer programs determine whether an apparition ties together earlier apparitions into a single orbit. If so, the object receives a catalog number and the observer of the first apparition with a calculated orbit is declared the discoverer, and granted the honor of naming the object subject to the approval of the International Astronomical Union.
Computerized methods.
There is increasing interest in identifying asteroids whose orbits cross Earth's, and that could, given enough time, collide with Earth. See Earth-crosser asteroids. The three most important groups of near-Earth asteroids are the Apollos, Amas, and 18s. Various asteroid deflection strategies have been proposed, as early as the 1960s. The near-Earth asteroid 433 Eros had been discovered as long ago as 1898, and the 1930s brought a flurry of similar objects. In order of discovery, these were 1221 Amma, 1862 Apollo, 2101 Adonis, and finally 69,230 Hermes, which approached within 0.005 AU of the Earth in 1937. Astronomers began to realize the possibilities of Earth impact. Two events in later decades increased the alarm: the increasing acceptance of Walter Alvarez's hypothesis that an impact event resulted in the Cretaceous-Paleogene extinction, and the 1994 observation of comet Shoemaker-Levy 9 crashing into Jupiter. The U.S. military also declassified the information that its military satellites, built to detect nuclear explosions, had detected hundreds of upper atmosphere impacts by objects ranging from 1 to 10 meters across. All these considerations helped spur the launch of highly efficient automated systems that consist of charge-coupled device, CCD, cameras and computers directly connected to telescopes. As of spring 2011, it was estimated that 89% to 96% of near-Earth asteroids 1 kilometer or larger in diameter had been discovered. A list of teams using such automated systems includes the Lincoln Near-Earth Asteroid Research, Linear, Team, the Near-Earth Asteroid Tracking, NEAT, Team, Spacewatch, the Lowell Observatory Near-Earth Object Search, LONEOS, Team, the Catalina Sky Survey, CSS, the Campo Imperatore Near-Earth Object Survey, CINEOS, Team, the Japanese Space Guard Association, the Asiago DLR Asteroid Survey, ADAS. The Linear system alone has discovered 138,393 asteroids, as of September 20, 2013. Among all the automated systems, 4711 near-Earth asteroids have been discovered, including over 600 more than 1 kilometer, 0.6 miles, in diameter.
Terminology.
Traditionally, small bodies orbiting the Sun were classified as asteroids, comets or meteoroids, with anything smaller than 10 meters across being called a meteoroid. the term asteroid is ill-defined. It never had a formal definition, with the broader term minor planet being preferred by the International Astronomical Union from 1853 on. In 2006, the term small solar system body was introduced to cover both most minor planets and comets. Other languages prefer planetoid, Greek for planet-like, and this term is occasionally used in English for larger minor planets such as the dwarf planets. The word planetesimal has a similar meaning, but refers specifically to the small building blocks of the planets that existed when the solar system was forming. The term planetule was coined by the geologist William Daniel Conybeare to describe minor planets, but is not in common use. The three largest objects in the asteroid belt, Ceres, 2 Pallas, and 4 Vesta, grew to the stage of protoplanets. Ceres is a dwarf planet, the only one in the inner solar system. When found, asteroids were seen as a class of objects distinct from comets, and there was no unified term for the two until small solar system body was coined in 2006. The main difference between an asteroid and a comet is that a comet shows a coma due to sublimation of near-surface ices by solar radiation. A few objects have ended up being dual-listed because they were first classified as minor planets but later showed evidence of cometary activity. Conversely, some, perhaps all, comets are eventually depleted of their surface volatile ices and become asteroids. A further distinction is that comets typically have more eccentric orbits than most asteroids. Most asteroids with notably eccentric orbits are probably dormant or extinct comets. For almost 2 centuries, from the discovery of Ceres in 1801 until the discovery of the first centaur, 2060 Chiron, in 1977, all known asteroids spent most of their time at or within the orbit of Jupiter, though a few such as 944 Hidalgo ventured far beyond Jupiter for part of their orbit. When astronomers started finding more small bodies that permanently resided further out than Jupiter, now called centaurs, they numbered them among the traditional asteroids, though there was debate over whether they should be considered as asteroids or as a new type of object. Then, when the first trans-Neptunian object, 1992 QB1, was discovered in 1992, and especially when large numbers of similar objects started turning up, new terms were invented to sidestep the issue: Kuiper belt object, trans-Neptunian object, scattered disk object, and so on. These inhabit the cold outer reaches of the solar system where ices remain solid and comet-like bodies are not expected to exhibit much cometary activity. If centaurs or trans-Neptunian objects were to venture close to the Sun, their volatile ices would sublimate, and traditional approaches would classify them as comets and not asteroids. The innermost of these are the Kuiper belt objects, called objects partly to avoid the need to classify them as asteroids or comets. They are believed to be predominantly comet-like in composition, though some may be more akin to asteroids. Furthermore, most do not have the highly eccentric orbits associated with comets, and the ones so far discovered are larger than traditional comet nuclei. The much more distant Oort cloud is hypothesized to be the main reservoir of dormant comets. Other recent observations, such as the analysis of the cometary dust collected by the Stardust probe, are increasingly blurring the distinction between comets and asteroids, suggesting a continuum between asteroids and comets rather than a sharp dividing line. The minor planets beyond Jupiter's orbit are sometimes also called asteroids, especially in popular presentations. However, it is becoming increasingly common for the term asteroid to be restricted to minor planets of the inner solar system. Therefore, this article will restrict itself for the most part to the classical asteroids, objects of the asteroid belt, Jupiter Trojans, and near-Earth objects. When the IAU introduced the class small solar system bodies in 2006 to include most objects previously classified as minor planets and comets, they created the class of dwarf planets for the largest minor planets, those that have enough mass to have become ellipsoidal under their own gravity. According to the IAU, the term minor planet may still be used, but generally the term small solar system body will be preferred. Currently only the largest object in the asteroid belt, Ceres, at about 950 kilometers, 590 miles, across, has been placed in the dwarf planet category, although there are several large asteroids, Vesta, Pallas, and Hygiea, that may be classified as dwarf planets when their shapes are better known.
Formation.
It is believed that planetesimals in the asteroid belt evolved much like the rest of the solar nebula until Jupiter neared its current mass, at which point excitation from orbital resonances with Jupiter ejected over 99% of planetesimals in the belt. Simulations and a discontinuity in spin rate and spectral properties suggest that asteroids larger than approximately 120 kilometers, 75 miles, in diameter accreted during that early era, whereas smaller bodies are fragments from collisions between asteroids during or after the Jovian disruption. Ceres and Vesta grew large enough to melt and differentiate, with heavy metallic elements sinking to the core, leaving rocky minerals in the crust. In the NICE model, many Kuiper belt objects are captured in the outer asteroid belt, at distances greater than 2.6 AU. Most were later ejected by Jupiter, but those that remained may be the D-type asteroids, and possibly include Ceres.
Distribution within the Solar System.
Various dynamical groups of asteroids have been discovered orbiting in the inner solar system. Their orbits are perturbed by the gravity of other bodies in the solar system and by the Yarkovsky effect. Significant populations include
Asteroid belt.
The majority of known asteroids orbit within the asteroid belt between the orbits of Mars and Jupiter, generally in relatively low eccentricity, that is not very elongated, orbits. This belt is now estimated to contain between 1.1 and 1.9 million asteroids larger than 1 kilometer, 0.6 miles, in diameter, and millions of smaller ones. These asteroids may be remnants of the protoplanetary disk, and in this region the accretion of planetesimals into planets during the formative period of the Solar System was prevented by large gravitational perturbations by Jupiter.
Trojans.
Trojan asteroids are a population that share an orbit with a larger planet or moon, but do not collide with it because they orbit in one of the two Lagrangian points of stability, L4 and L5, which lie 60 deg ahead of and behind the larger body. The most significant population of Trojan asteroids are the Jupiter Trojans. Although fewer Jupiter Trojans have been discovered as of 2010, it is thought that they are as numerous as the asteroids in the asteroid belt. A couple of Trojans have also been found orbiting with Mars.
Near-Earth asteroids.
Near-Earth asteroids, or NEAs, are asteroids that have orbits that pass close to that of Earth. Asteroids that actually cross the Earth's orbital path are known as Earth crossers. As of May 2010, 7,075 near-Earth asteroids are known and the number over 1 kilometer in diameter is estimated to be 500 to 1,000.
Characteristics. Size distribution.
Asteroids vary greatly in size, from almost 1,000 kilometers for the largest down to rocks just tens of meters across. The three largest are very much like miniature planets, they are roughly spherical, have at least partly differentiated interiors, and are thought to be surviving protoplanets. The vast majority, however, are much smaller and are irregularly shaped. They are thought to be either surviving planetesimals or fragments of larger bodies. The dwarf planet Ceres is by far the largest asteroid, with a diameter of 975 kilometers, 610 miles. The next largest are 2 Pallas and 4 Vesta, both with diameters of just over 500 kilometers, 300 miles. Vesta is the only main belt asteroid that can, on occasion, be visible to the naked eye. On some rare occasions, a near-Earth asteroid may briefly become visible without technical aid. See 99,942 Apophis. The mass of all the objects of the asteroid belt, lying between the orbits of Mars and Jupiter, is estimated to be about 2.8-3.2 x 1021 kg, or about 4% of the mass of the Moon. Of this, Ceres comprises 0.95 x 1021 kg, a third of the total. Adding in the next three most massive objects, Vesta, 9%, Pallas, 7%, and Hygiea, 3%, brings this figure up to 51%. Whereas the three after that, 511 Davida, 1.2%, 704 Interamnia, 1.0%, and 52 Europa, 0.9%, only add another 3% to the total mass. The number of asteroids then increases rapidly as their individual masses decrease. The number of asteroids decreases markedly with size. Although this generally follows a power law, there are bumps at 5 km and 100 km, where more asteroids than expected from a logarithmic distribution are found.
Largest asteroids.
Although their location in the asteroid belt excludes them from planet status, the four largest objects, Ceres, Vesta, Pallas, and Hygiea, are remnant protoplanets that share many characteristics common to planets, and are atypical compared to the majority of potato-shaped asteroids. Ceres is the only asteroid with a fully ellipsoidal shape and hence dwarf planet. Vesta has, aside from the large crater at its southern pole, Rheasilvia, an ellipsoidal shape. Ceres has a much higher absolute magnitude than the other asteroids, of around 3.32, and may possess a surface layer of ice. Like the planets, Ceres is differentiated. It has a crust, a mantle and a core. Vesta, too, has a differentiated interior, though it formed inside the Solar System's frost line, and so is devoid of water. Its composition is mainly of basaltic rock such as olivine. Pallas is unusual in that, like Uranus, it rotates on its side, with its axis of rotation tilted at high angles to its orbital plane. Its composition is similar to that of Ceres, high in carbon and silicon, and perhaps partially differentiated. Hygiea is a carbonaceous asteroid and, unlike the other largest asteroids, lies relatively close to the plane of the ecliptic.
Rotation.
Measurements of the rotation rates of large asteroids in the asteroid belt show that there is an upper limit. No asteroid with a diameter larger than 100 meters has a rotation period smaller than 2.2 hours. For asteroids rotating faster than approximately this rate, the inertia at the surface is greater than the gravitational force, so any loose surface material would be flung out. However, a solid object should be able to rotate much more rapidly. This suggests that most asteroids with a diameter over 100 meters are rubble piles formed through accumulation of debris after collisions between asteroids.
Composition.
The physical composition of asteroids is varied and in most cases poorly understood. Ceres appears to be composed of a rocky core covered by an icy mantle, where Vesta is thought to have a nickel-iron core, olivine mantle, and basaltic crust. Hygiea, however, which appears to have a uniformly primitive composition of carbonaceous chondrite, is thought to be the largest undifferentiated asteroid. Most of the smaller asteroids are thought to be piles of rubble held together loosely by gravity, though the largest are probably solid. Some asteroids have moons or are co-orbiting binaries, rubble piles, moons, binaries, and scattered asteroid families are believed to be the results of collisions that disrupted a parent asteroid. Asteroids contain traces of amino acids and other organic compounds, and some speculate that asteroid impacts may have seeded the early Earth with the chemicals necessary to initiate life, or may have even brought life itself to Earth. See also panspermia. In August 2011, a report, based on NASA studies with meteorites found on Earth, was published suggesting DNA and RNA components, adenine, guanine and related organic molecules, may have been formed on asteroids and comets in outer space. Composition is calculated from three primary sources: albedo, surface spectrum, and density. The last can only be determined accurately by observing the orbits of moons the asteroid might have. So far, every asteroid with moons has turned out to be a rubble pile, a loose conglomeration of rock and metal that may be half-empty space by volume. The investigated asteroids are as large as 280 km in diameter, and include 121 Hermann, 268 x 186 x 183 km, and 87 Sylvia, 384 x 262 x 232 km. Only half a dozen asteroids are larger than 87 Sylvia, though none of them have moons. However, some smaller asteroids are thought to be more massive, suggesting they may not have been disrupted, and indeed 511 Davida, the same size as Sylvia to within measurement error, is estimated to be 2.5 times as massive, though this is highly uncertain. The fact that such large asteroids as Sylvia can be rubble piles, presumably due to disruptive impacts, has important consequences for the formation of the Solar System. Computer simulations of collisions involving solid bodies show them destroying each other as often as merging, but colliding rubble piles are more likely to merge. This means that the cores of the planets could have formed relatively quickly. On October 7, 2009, the presence of water ice was confirmed on the surface of 24 Themis using NASA's Infrared Telescope facility. The surface of the asteroid appears completely covered in ice. As this ice layer is sublimated, it may be getting replenished by a reservoir of ice under the surface. Organic compounds were also detected on the surface. Scientists hypothesize that some of the first water brought to Earth was delivered by asteroid impacts after the collision that produced the Moon. The presence of ice on 24 Themis supports this theory. In October 2013, water was detected on an extrasolar body for the first time, on an asteroid orbiting the white dwarf star GD61.
Surface features.
Most asteroids outside the Big Four, Ceres, Pallas, Vesta, and Hygiea, are likely to be broadly similar in appearance, if irregular in shape. 50 km, 31 mile, 253 Matilda, shown at right, is a rubble pile saturated with craters with diameters the size of the asteroid's radius, and Earth-based observations of 300 km, 186 mile, 511 Davida, one of the largest asteroids after the Big Four, reveal a similarly angular profile, suggesting it is also saturated with radius-sized craters. Medium-sized asteroids such as Matilda and 243 Ida that have been observed up close also reveal a deep regolith covering the surface. Of the Big Four, Pallas and Hygiea are practically unknown. Vesta has compression fractures encircling a radius-sized crater at its south pole but is otherwise a spheroid. Ceres seems quite different in the glimpses Hubble has provided, with surface features that are unlikely to be due to simple craters and impact basins, but details will not be known until dawn arrives in 2015.
Color.
Asteroids become darker and redder with age due to space weathering. However, evidence suggests most of the color change occurs rapidly, in the first 100,000 years, limiting the usefulness of spectral measurement for determining the age of asteroids.
Classification.
Asteroids are commonly classified according to two criteria: the characteristics of their orbits, and features of their reflectance spectrum.
Orbital classification.
Many asteroids have been placed in groups and families based on their orbital characteristics. Apart from the broadest divisions, it is customary to name a group of asteroids after the first member of that group to be discovered. Groups are relatively loose dynamical associations, whereas families are tighter and result from the catastrophic breakup of a large parent asteroid sometime in the past. Families have only been recognized within the asteroid belt. They were first recognized by Kiyoshigu Hirayama in 1918 and are often called Hirayama families in his honor. About 30 to 35% of the bodies in the asteroid belt belong to dynamical families, each thought to have a common origin in a past collision between asteroids. A family has also been associated with a Plutoid dwarf planet Haumea.
Quasi-satellites and horseshoe objects.
Some asteroids have unusual horseshoe orbits that are co-orbital with the Earth or some other planet. Examples are 3753 Cruithne and 2002 AA29. The first instance of this type of orbital arrangement was discovered between Saturn's moons Epimetheus and Janus. Sometimes these horseshoe objects temporarily become quasi-satellites for a few decades or a few hundred years, before returning to their earlier status. Both Earth and Venus are known to have quasi-satellites. Such objects, if associated with Earth or Venus or even hypothetically Mercury, are a special class of 8 asteroids. However, such objects could be associated with outer planets as well.
Spectral classification.
In 1975, an asteroid taxonomic system based on color, albedo, and spectral shape was developed by Clark R. Chapman, David Morrison, and Ben Zellner. These properties are thought to correspond to the composition of the asteroid's surface material. The original classification system had 3 categories: C types for dark carbonaceous objects, 75% of known asteroids; S types for stony, silicaceous objects, 17% of known asteroids, and U for those that did not fit into either C or S. This classification has since been expanded to include many other asteroid types. The number of types continues to grow as more asteroids are studied. The 2 most widely used taxonomies now used are the Tholen classification and SMASS classification. The former was proposed in 1984 by David J. Tholen, and was based on data collected from an 8-color asteroid survey performed in the 1980s. This resulted in 14 asteroid categories. In 2002, the Small Main Belt Asteroid Spectroscopic Survey resulted in a modified version of the Tholen taxonomy with 24 different types. Both systems have 3 broad categories of C, S, and X asteroids, where X consists of mostly metallic asteroids, such as the M-type. There are also several smaller classes. The proportion of known asteroids falling into the various spectral types does not necessarily reflect the proportion of all asteroids that are of that type. Some types are easier to detect than others, biasing the totals.
Problems.
Originally, spectral designations were based on inferences of an asteroid's composition. However, the correspondence between spectral class and composition is not always very good, and a variety of classifications are in use. This has led to significant confusion. Although asteroids of different spectral classifications are likely to be composed of different materials, there are no assurances that asteroids within the same taxonomic class are composed of similar materials.
Exploration.
Until the age of space travel, objects in the asteroid belt were merely pinpricks of light in even the largest telescopes, and their shapes and terrain remained a mystery. The best modern ground-based telescopes and the Earth-orbiting Hubble Space Telescope can resolve a small amount of detail on the surfaces of the largest asteroids, but even these mostly remain little more than fuzzy blobs. Limited information about the shapes and compositions of asteroids can be inferred from their light curves, their variation in brightness as they rotate, and their spectral properties, and asteroid sizes can be estimated by timing the lengths of star occultations, when an asteroid passes directly in front of a star. Radar imaging can yield good information about asteroid shapes and orbital and rotational parameters, especially for near-Earth asteroids. In terms of delta-V and propellant requirements, NEOs are more easily accessible than the Moon. The first close-up photographs of asteroid-like objects were taken in 1971 when the Mariner 9 probe imaged Phobos and Deimos, the 2 small moons of Mars, which are probably captured asteroids. These images revealed the irregular, potato-like shapes of most asteroids, as did later images from the Voyager probes of the small moons of the gas giants. The first true asteroid to be photographed in close-up was 951 Gaspra in 1991, followed in 1993 by 243 Ida and its moon Dactyl, all of which were imaged by the Galileo probe en route to Jupiter. The first dedicated asteroid probe was near Shoemaker, which photographed 253 Matilda in 1997, before entering into orbit around 433 Eros, finally landing on its surface in 2001. Other asteroids briefly visited by spacecraft en route to other destinations include 9969 Braille, by Deep Space One in 1999, and 5535 Anne Frank, by Stardust in 2002. In September 2005, the Japanese Hayabusa probe started studying 25,143 Itokawa in detail and was plagued with difficulties. but returned samples of its surface to Earth on June 13, 2010. The European Rosetta probe, launched in 2004, flew by 2867 Steins in 2008 and 21 Lutetia, the second-largest asteroid visited to date, in 2010. In September 2007, NASA launched a Dawn mission, which orbited the protoplanet 4 Vesta from July 2011 to September 2012, and is planned to orbit 1 Ceres in 2015. 4 Vesta is the largest asteroid visited to date. On December 13, 2012, China's lunar orbiter Chang'e 2 flew within 2 miles, 3.2 kilometers, of the asteroid 4179 Tautatis on an extended mission. The Japan Aerospace Exploration Agency, JAXA, plans to launch around 2015 the improved Hayabusa 2 space probe and to return asteroid samples by 2020. Current target for the mission is the C-type asteroid, 162,173, 1999 Ju-3. In May 2011, NASA announced the OSIRIS-REx sample return mission to asteroid 1999 RQ-36, and is expected to launch in 2016. On February 15, 2013, an asteroid measuring approximately 18 meters, 59 feet, with a mass of about 9,100 tons, 10,000 short tons, exploded over Chelyabinsk, Russia, causing 1,500 injuries and damaging 7,000 buildings. Small samples of the rocky Chelyabinsk meteorite were quickly recovered and analyzed, with a larger fragment found several months later. In early 2013, NASA announced the planning stages of a mission to capture a near-Earth asteroid and move it into lunar orbit, where it could possibly be visited by astronauts and later impacted into the Moon. It has been suggested that asteroids might be used as a source of materials that may be rare or exhausted on Earth, asteroid mining, or materials for constructing space habitats. See colonization of the asteroids. Materials that are heavy and expensive to launch from Earth may someday be mined from asteroids and used for space manufacturing and construction.
Fiction.
Asteroids in the asteroid belt are a staple of science fiction stories. Asteroids play several potential roles in science fiction, as places human beings might colonize, resources for extracting minerals, hazards encountered by spaceships traveling between 2 other points, and as a threat to life on Earth by potential impact.